Have stuff to talk about on transmissions and on Valvetrain. So stop me wherever anybody has any questions. I intended this whole thing to be together just as kind of a guide to make sure I hit through a lot of points on it, but I'm not going to read every bullet point and go through every detail on it. That wasn't my intent. So just general on the transmissions, right? There's the same transmissions, 1G, 2G, front wheel drive, all wheel drive. The guts for the most part are all the same strength on those, and most of those parts interchange. Converter and pump, you'd have to swap for that's background noise. Converter and pump are different between them, but pretty much all the rest of the guts interchange. Converter, pump, input shaft. So there's no real reason to choose one over another aside from things like what torque converter you're going to run. There's better converter options for the 2G. Biggest thing on the transmissions compared to a 5-speed, and I know a lot of the DSMs are on autos now, but the biggest thing is heat and making sure you manage the heat. There's also a lot bigger losses in the auto trans. They'll dyno 15-20% less than a 5-speed. Don't be scared of that. They still generally will run a better ET for the same engine power. One thing here, just to show kind of characteristic temperatures on it, right? We got like 200 degrees or so, going up to 350. This is kind of a high 7-second pass out of our drag car. That is pretty normal on the converter outlet temperatures to see them go up that much if you've got an actual high-speed thermocouple in there. So this amount of temperature will not actually burn the fluid. Usually I'm running John Deere high guard fluid. Usually that is what I run in it, is that. And if you burn the fluid, it got hotter than this. So it doesn't matter if you saw 180 in the pan. The spot that it got hottest is what your issue would be. Got just general info on how an automatic transmission works. Right, we've got a pump at the front of it that generates pressure. There's a valve body that controls where that pressure goes. There's a whole series of clutch packs that have splines inside and outside fuses hooked together that then run to the planetary gear set, and different parts of the planetary engaged make different gears happen. So there's not much more to it than that. All automatic transmissions for the most part work very, very similarly. The DSM Autotrans has a Ravino. It's this stacked 2-stage planetary gear set that the cars that are in the 7s have started fighting considerably. Ford C4 has that same gear set. Not many other types of automatic transmissions run that architecture. Most of them just have single planets. But relatively unique structure on this, so it'd be tricky to make parts for it because it's a little bit weird. So, torque converter efficiency curve here. Basically, the torque converter acts like a CVT whenever you're not engaged in a gear, after you shift in a gear, you'll see RPMs higher than if you did a calculated, what was my first to second gear drop. That would be way more than that because you're riding on the torque converter, it's multiplying torque, acting like a CVT, and keeping the engine in the power band if you've got a combo that works well.
Pause for 1 second.
Oh, yeah, sorry, we need a break.
Yes, let's take about 7 seconds.
They can watch this too. Which one's taller?
That's not a burn.
I'll just move it. Just tap this.
It's alright.
Pull the chute.
Alright. And that's why we're all here.
Cause I wanna do that.
Awesome, so here's parts that Devin's not using whatsoever. So from a automatic point of view, right, you've got a torque converter, and everybody wants a converter that's gonna be as loose as possible down low and as tight as possible up top. Well, you don't really get that. There's no free lunch in it. There's a little bit that you can vary on that, but basically if it's loose down low, it's gonna be loose up top. What I've been doing on the drag car, and what, you know, Aaron's gone this route as well, we keep going tighter and tighter on the converters to get them tight enough up top that we're not dealing with huge amounts of slip. Like the precision steps, like, you know, this is kind of your torque behavior. So if you've got 800 foot-pounds of torque, you'd be stalling at these different speeds, you know, anywhere from 5,500 to 8,000 RPM with the examples shown here. With the laser, we were on, the progression goes at 8, a 7, a 6, a 0, and then a 4. We were on a 4. So the 4 is actually somewhere in the range of a restalled stock converter. So you end up having to work around a lot of things to get a setup that's going to be able to make boost at low enough RPM, or be able to run enough nitrous to get it up on the converter, and still be tight enough that at the top end you're not dealing with 20% slip and seeing your trans temperatures go up to, you know, 400 to 500 degrees and burning stuff up. Because that also is what feeds the planetary, and that's another, you know, weak link within this transmission. Really, once you start getting down into the 7s, if you're talking an 8-second car or so, the planetary lives pretty okay. Any questions on converters, anything with that?
So number 4 is the tightest one they offer?
Number 4 is the first one in the looseness of what they put behind a big block. And they normally don't put that with a 4-cylinder combo. So they have stuff that's tighter than that. I don't know what the numbers are after that. But yeah, for example, on mine, I was seeing with a 0 on the 2-3 shift, when it was at, I had a couple runs where it was with 85 shot of nitrous on and 80 pounds of boost, and it would pull the engine down to 9,300 RPM. And that's it. That's all it would pull it down to. So it's just breathing fire at that point.
And that's on the number 4?
That was on the 0.
Oh.
So the
okay.
4 is tighter than that. So.
Yeah.
Yeah, you basically, there's a fine line between loose enough that it spools up nice and drives awesome, and too loose that it slips too much up top and you're dealing with temperature and trap speed losses because of it just blowing through the converter. So there's a balancing act there. Fortunately, there's a lot of things to do to tune it. You know, there's a lot of different options within there, specifically within the precision stuff, but you can go wrong. Good first 3 feet there. So strength within different parts of the transmission. Splines, most of the splines are good within this trans as long as you're not using 4th gear. Most of the normal parts within this trans live okay and do kind of a mid 8-second car. As you start getting faster than that, you'll break the rear clutch, the hub on the rear clutch. Jeff Bush has JB Designs, and Jeff Bush has a part for that is made out of steel instead of iron, and then the splines don't break. And then also the input shaft. We've seen some input shafts snap the end off the input shaft, so there's a 300M input shaft for that as well. I haven't seen anyone break either of those 2 parts. And the rest of the splines in the trans, really, we see wear sometimes on a kickdown drum, but that doesn't seem to be related to power. It's just related to mileage on a car, so you just find a good one, it'll be okay. And the other spline that's in it is the end clutch spline, and that thing's just a joke. It's a tiny little thing, and you can't run 4th gear past 500 horsepower. So gears. I would recommend at really any level that you're whooping on these that you go to the straight cut gears. The helical transfer gears, the big 3 gears. So from the primary drive to the secondary to the one that's on the center diff in an all-wheel drive car. Those in a street car, if you wheel hop at all, it'll crack them, it'll break them. Drag car, if you're talking something that can do 460 foots, it's limited life. And when they go, it is a mess. They usually jam up against each other. They're really close to the case. They blow the case open. you got 11 quarts of trans fluid on the track. You have no friends left after that. It's a really bad walk of shame moment. So the Liberty gears, Liberty makes gears for it. There's a few different places you can get them through. They are reliable. No one's broken those, and you can get them in longer gear ratio. So a lot of people, you'll run out of gear depending on what you're revving the engine to. You can run out of gear before the end of the quarter mile at a 10,000 RPM limiter. So the 7% extra can help on that a good bit.
Question.
Yeah.
If you had a street application where you wanted to do the automatic in there,
Yeah.
with straight cut gears, is that just first through third?
So they're all the drive gears.
All
So
the drive
it's at the
gears,
end of the primary stack where all the shifting happens, and it's they transfer from the primary stack out to the final drive.
Okay.
So yeah, they're running all the gears.
Is it a lot noisier once you change it?
It's not bad. You'll hear it, but
Okay.
it's not. I don't know. It's not like old muscle car gear drive cam loud.
Okay.
But you do hear it. So I don't think anyone's building a DSM because they want it to be plush
Quiet,
and cushy.
yeah.
So, they're not super objectionable.
Gotcha.
We were starting to break ring gears in the front wheel drive by high sevens. They would last maybe a season or so and start showing up cracks on them and then break them. The front wheel drive ring gear is different than the all wheel drive. It's bigger and coarser teeth, so it is a bit stronger. But that was kind of the next weak link. I don't know that that's important to anybody else but me, but that's what we have there. Case, generally, not really any issues with the case. The only things there were front wheel drive, and if they got into tire shake, we'd break them out. So I was welding a bunch of stuff on to brace up the back of the case, and probably went through half dozen iterations before I got it strong enough that it wouldn't break if it hopped out of a burnout or shook the tires hard. Any questions on strength of the parts if you're building one of these? Okay. Clutches. What time on that? So clutches are definitely the weak link within this transmission to make sure you've got the right stuff in there. The first thing that you will run into trouble with slipping is the front clutch. It's the lowest torque capacity of the whole transmission, and it also does not have a super great way that fluid is applied to it. The fluid built to it is pretty slow, and that ends up resulting in a lot of wear on it for its size, and it's just the first weak link within it. So the factory for friction in it, if you have a shift kit in it, TransLab is what we generally do for anything on that. You will see that kind of on all factory guts and just with the shift kit, we've seen a bunch of people go 10s as long as you're shifting it at full line pressure, even bottom 10s, and they last okay at that. So, it's kind of we were junkyard dropping things in before LSs, right? So, but they live all right with that. After that, we've got a 5 friction and 6 friction clutch pack for that, and then there's the billet 6 friction that we have, which has a bigger piston, which then increases the clamp on the clutch and makes it more capable than just the regular 6 friction. So I think that, I don't have the number here, I think it was around double the torque capacity of a stock 4 friction by the time you're at the bigger piston with the 6 friction. Next thing we see was the band would slip. That tended to be kind of high 7s with the TransLab shift kit at 180 psi. So after that, we started either shimming springs or going to a different spring so that we could get the line pressure up above 200 psi. But yeah, the normal just drop-in shift kit, the band starts to be a weak link somewhere around A flat, high 7s. There's one clutch that's got too much capacity in it that we pull a couple of clutches out of. You guys have no idea where my cursor is. I will point. The rear clutch, or sorry, low reverse brake, which is this guy that's around the planetary. Thing's, yay big in diameter, and the thing is spinning the inside of it at the same as the planetary speed is. So in third gear, it could be spinning at 9,000 RPM with the case static. So that one has more capacity than you need, so we take the frictions out of that because even with 4 frictions in it instead of 6, still never see wear on it. It's used in reverse. I wouldn't do big brake torques in reverse with them out, but no, I'm gonna do that anyway. Anyway, that's one that helps out a little. You got to make sure that you fill the space with steel, so otherwise you'll overextend the piston and blow the seal out. Yeah, and then the rear and end clutches generally aren't an issue unless something else has gone wrong. We had points where we had, 5 seasons on a rear clutch friction set, didn't show anywhere.
Regarding the 5 friction front clutch,
Yes.
at what point, a lot of people are running those into the 8s and
Yeah.
having a lot of successes at it. So it's not necessarily something that you need to upgrade to the big billet front clutch right away.
Yeah.
Or anything like that. I mean, 5 friction was pretty stout for most applications.
Yeah, thanks. Another really important thing on that is if in an auto trans, if you wear clutches out, it's not the end of the world. It doesn't take anything else out. It puts dirt in the fluid, put new frictions in it, it'll be okay. We have several customers that have run high 7s on the 5 friction or the 6 friction in the factory basket. It's really when you're talking, really bottom 8s that you need to start looking at the billet unit. So, yeah, I think we've had 3-4 people that have run high 7s on the 5 friction within the factory basket. So, any questions on clutches and setup on that? Most of them don't care much about clearance for what it's worth. We haven't seen much difference if you're anywhere from 4 or 5 thou per friction to 10 thou per friction. They're not very fussy about it. General tips on this, use a shift kit. Always important to have a shift kit in it to get appropriate pressure to everything. Make sure you're running one of the dual inlet metal filters. I think Mitsubishi still makes some, but Napa definitely does. The plastic filters are a mess. They're very restrictive when we were running those, and looking at line pressure, after you got to a high enough RPM, you would see line pressure just tank, and that's just take stuff out at that point. So, porting the valve body is important as well. We've got some pictures on the website. There's some really kind of sharp cornered passages as the fluid comes up from the valve, from the filter into the valve body. There's a couple sharp turns that there's enough material that you can kind of soften those a lot and make it flow better. Very, very important to launch on a 2-step. I think everyone, for the most part, gets that nowadays, but there was a very long time that people were not using 2-steps to launch with autos, and they'd get stuck on the tree for a while, and they'd be at 35 pounds of boost and 5,500 RPM, and then they'd get rolled back. Yeah, appropriate 2-step should be where it just starts to turn the tires over, and then you set the boost by what anti-lag you're running. Run a filter on the cooler lines. In these transmissions, we sometimes see the converter cavitation within the converter generating a little bit of debris, and that then gets put through the cooler back into the pan, and then eventually makes it into the works of the trans again, and that will result in valve body problems and things sticking within the valve body. So make sure you run a filter on that. Magnifine has some nice 6AN filters. You can get like just an automotive remote oil filter kit and put AN lines to it and run a spin-on frame filter. Things like that work fine. The crankshaft and flex plate and converter combo can be difficult to keep tight. The reason we make an 8-bolt flex plate is because we couldn't get anything to hold with a 6-bolt flex plate after maybe 500-600 wheel horsepower, somewhere in there. So that joint on a 4-cylinder is very, very difficult. 4 cylinders go through massive torque reversals. They torque forward and torque backward during a revolution. 4 cylinders are actually the absolute worst combination in the world of any number of cylinders to get to that. So it's worse with RPM than it is with load, but both you can overload that joint and then you end up with loose bolts. Sounds like you lost a rod, but get in there and check out the bolts. So yeah, 8-bolt converter on anything above about 500 horsepower, usually go to 50-55 foot-pounds, red Loctite on it. Crankshaft is tricky as well. We're looking at some other things to help us out, but right now the best solution on that is gluing the flex plate to the crankshaft with Loctite, and then torquing the bolts basically as high as you're comfortable with. We generally recommend 130 foot-pounds. Red Loctite on those as well. I've gone as high as 150 on the drag car, but I cringe every time I do that. So, have some details here that are things probably not worth talking through in detail, but reference for later on stuff that can be eliminated in the transmission when it's used as a 3-speed. So there are several valves in it that you just don't need. They don't do anything anymore. You don't want them to move from the spot that they start in. So lock them in that spot, and it's fine as a 3-speed. So this is the guide to do that. And also, the 1-2 shift can sometimes have a little bit of binding on it, and the info here helps out with that. It delays the band being applied in second gear until the low reverse brake has a chance to exhaust the pressure from that and release. Otherwise, you've got 2 gears trying to grab it once. It speeds up on everything.
Couple things here. Excuse me, sir.
Yeah.
Regarding the transmission chips, Translab shift kit, they seem to have a couple, or at least they used to. Make sure you spec the one that has the dash HP after it. I believe the whole part number is STL, like 175. They have some that don't have the HP, and they have the one with the HP. We need the one with the HP because it's missing the springs, right?
Yeah, thank you. There's a couple springs. There's also a couple drills and drill sizes for the separator plates. It doesn't come with like the black spring and a couple of the other high performance
Make
springs.
sure.
I think it had 3 lines on that actually.
Okay.
So
Right, and then one other thing, regarding the flex plate, retorquing after you have it installed after a couple of heat cycles. You can do that right at the track, 2 people, just retorquing the converter bolts, just to make sure, especially if it's a new install.
yeah, another thing to help out with that. Thank you. A lot of the places paint converters. They paint both sides of it. They get a bunch of paint in the threads. But when paint gets hot, it gets really soft. And there's very little stretch on those bolts. It's a very small joint. So best thing to do there, run a tap into each of the bolt holes, try and clean all the paint out of them. Razor blade to the pads, get the paint off the pads where it touches the flex plate. That's your best first start to getting that joint to live. Things we've been doing so a lot of the info there was stuff that probably 80% of it we've had in some of the older tech talks that we had on the Facebook group, and we're gonna put this on the Kiggly Racing website so people can download it and grab it. But this is all kind of new stuff over the last few years. One of the things we've seen as the cars go into kind of high 7s is the planetary is really hard to keep from overheating it and also from just overloading it. And oil pressure to that planetary is very, very important. So in the factory system, the oil comes out of the converter, goes through the cooler, and then it goes to the planetary. And this is a log from, I don't know, 6 years ago or so with the factory oiling. This is about 50 psi, 50, 60 psi. See, it drops down to as low as 30 to 40 psi. That's with the factory oiling setup. In the high power, high RPM applications, it can make sense to start looking at taking oil directly from the reducing port. There's check ports on the bottom of the trans, and you can go from the reducing port directly to the planetary, and then instead of the converter oiling the planetary, it comes from that reducing port, and you can then dump the oil from the converter right into the pan. That's what this other purple graph is here. That's more so 100 to 120 psi. The planetary gears live considerably better with that at these levels. Kind of mid-8s or so is where this starts to show up a bit. By high 7s, it's kind of ugly. So, what else? We've seen a couple areas where looked at changing pressure to the converter. For a while, I was recommending to run full pressure to the converter. That doesn't seem to make much of a difference on converter performance from full pressure to regulated pressure. There's an orange spring in the Translab shift kit for that. So that reduces the load on the thrust bearing in the engine. Seems to be a little better to do that. So for a while we were chasing converter slip with higher pressure, and it seemed to be a bit of a dead end. So no need to add the load into the trans for that, or into the engine. Another thing here, this is a third gear shift. So this is a front clutch pressure rise trace. You'll see it takes about 1.5 seconds from the start of pressure build until full pressure. That is very characteristic of these transmissions. They take a very long time to apply pressure to third gear. And while I don't really have a fix for what architecture in the valve body would need to be changed for that, that's just kind of the reality we have on that. And It's why third gear on these is not as sharp as like the 1-2 shift can be. Also, at 10,000 RPM plus stuff and 60 plus pound of boost stuff, we have seen some of the encoders on the top of the trans that we use for shifting. I've also seen those lose contact and do wacky stuff. So at that kind of level, I would also recommend going to electronic shifted, whether it's one of the boxes made like a Force 4 box, something like that, or ECM shifting it. It's a good way to go. Only got about 5 minutes left here. That's all I had on transmissions. Next stuff I've got's on Valvetrain. Any questions on transmissions before I start talking about the things that open and close?
I have a million questions, I just don't know how to ask them.
Alright. Go by the booth later. Think of them. Alright, just take a quick run through on some Valvetrain stuff here. So on this, intake valves are mainly controlled by or limited by RPM, the cam profile, and the mass of the Valvetrain system. For us, generally, RPM is not a huge limiter on the intake side. You have to have enough spring and enough seat pressure to work along with that, but usually on the intake side, it's pretty predictable, and definitely have combos that we've seen people do 11,000 RPM with without any issues. You start going above that, valve tips get ugly. Here's just a curve of lift profile. This is the calculated force that you would see inside of the Valvetrain, at the valve tip. At 11,000 RPM, this is just a typical cam profile that would be similar to what a lot of people are running, maybe 280, 288-ish, somewhere in there. It's not exactly any of those, but it's very similar. You'll see a peak force at around 600 pounds as that intake valve is getting slapped open. So that's like your peak rocker load that you'd see in that system. And everything's pretty predictable. This is some combustion intake and exhaust port pressure traces here. There's usually very little pressure difference across the valve during intake valve opening or intake valve closing. So there's no real significant forces that show up from that. Okay? Exhaust, not so much. Exhaust is gross. So exhaust has everything I just said there for the intake going on, except it's got to open against cylinder pressure. So this graph here was a dyno pull at about 60 pounds of boost. It's actually the same as the previous pull was, it's just the whole cylinder pressure trace along with it. And the exhaust valve has to open in this case against about 1,300 PSI worth of cylinder pressure. So to actually pop open against that, you have to overcome the amount of force that pressure makes on the projected area of the valve, which is about 1 square inch. So really, that makes 1,300, 1,400 pounds worth of force there, plus whatever seat pressure you're running. So you're talking a solid 2.5 times the amount of force that you would have on the intake side. So if you're gonna see things get beat up on rockers and Valvetrain things, this is why the exhaust lives a harder life, is because it's gotta open against that cylinder pressure. So this gets exaggerated the bigger the exhaust cam is and the earlier you have your exhaust valve opening event happen, which also ties into usually power potential. So it's got teeth on both sides of it. We've seen rockers break, kind of start getting past 60, 70 PSI, or any amount of nitrous along with that, and this number just keeps going up. So we've seen, generally the first thing that happens is the roller will split. So if you hear something ticking from the top end of the engine, roll it over, look for split rollers. It's a lot better to catch it then than when it drops all the needle bearings into the oil pan. Any questions on that for just what exists?
Force increase if you're using solid lifters in that case as well?
No, it doesn't. The force should stay the same there because it's really just what the cylinder pressure is. So solid lifters, the only real difference we've seen on those is not many people make a cam profile for this engine that is designed for solid lifters, and you do different take-up ramps, both at the opening side and the closing side, that like just barely take up the slack before it starts to go into the lift event. And on a hydraulic lifter cam profile, they just go right into that event. So if you run a solid lifter on a hydraulic profile, it's the start of it has it smacks it instead of gently moves it. So you tend to see the the spring get excited more, the spring will wobble a bit more, and you'll see quicker spring wear, basically. Running over here, but as long as you're alright. Spring pressure. So, springs and spring pressure. So, we use beehive springs because they're variable frequency as they get compressed. The frequency that they ring at when they're extended compared to when they're compressed is different because the geometry changes as different coils close to a certain amount. A straight diameter spring usually has a single frequency, and it doesn't matter how much it's compressed, it stays at that same frequency. So if it starts to ring, then you can get into more of a standing wave in the spring, where the beehive spring does a better job of deadening out that standing wave, and that's why all of our product line is that. Seat pressure, 1.7 times absolute pressure in the manifold. You only need seat pressure to keep the valves closed, but the returning pressure waves that happen in headers and in intake systems can pop valves open, especially if you have a header length that has a high pressure wave that comes back in the middle of the intake stroke. We usually will see this more on the exhaust side than on the intake side. Really, the rule of thumb that we've had here, that I can fit a little bit of theory to it, but it works well, the 1.7 times absolute. So if you've got 60 PSI boost, you'd want 127 pounds on the seat. You'll be safe with that. We've seen people get away with a lot less than it, but this rule works really well for that. Another thing we found over the last couple years, unfortunately, is don't do boost cuts, or don't do ignition cuts at high boost. Traction control events and that, the booms and bangs that you see out of it, those are really cool. Nice flames out of it, but when that happens, what happens is the air-fuel mixture makes it out of the chamber, makes it through the header, hits the turbine wheel ignites it, and then it zings back a very high pressure wave to the valve. During combustion, we see generally about a 6-to-1 pressure rise just from combusting an air-fuel mixture. So what you get then is you get a 6-to-1 pressure rise of that exhaust back pressure right back to the valve. So you can very easily, if you've got 50 PSI back pressure, which is pretty easy to get at 40, 50, 60 PSI boost, you're gonna see a 300 PSI pressure spike, which would take a seat force on the valves that is just absolutely unattainable to achieve. So you can blow a valve full open, rocker comes off, bad stuff can happen. So traction control by ignition cut is really beats the hell out of everything.
So you would do it fuel cut then?
Yeah, fuel cut would be safer from a Valvetrain point of view. I haven't dove that. You're better off just doing things that will keep it out of that much spin, or pedaling it. But fuel cut has its own scary things as well. Yeah. So.
Dang if you do, dang if you don't.
Yeah. So don't overpower it too bad, or you're gonna have trouble. This is the last one. We get a lot of questions on hydraulic lash adjusters and how they work, and when do I need solid lifters, and how much pressure do I need to the lash adjusters for them to work. This is actually out of the DSM Tech manual. So the bottom section of this is a high pressure chamber with a check valve on it that oil is simply sitting on top of, and then it bleeds into there whenever the spring pushes the whole system, the whole center stack up. The whole way that the entire lifter works is the pressure that you apply to the lifter only fills a reservoir that then keeps fluid available for that high pressure chamber to do its work. So the amount of pressure that you actually have to the lifter really doesn't impact the lower part of its function. Higher pressure you can have areas where there could be more turbulent and more entrained air within oil. As you increase pressure with oil, air is more soluble in it, so it could be springier with higher pressure, but as long as there's any pressure to it, you're good from a lifter point of view. The solid lifter side of it, in the drag car we were running hydraulic lifters.
So that pop was more than likely caused from what you were talking about.
That's an ignition cut. Yeah, those are the noises you don't want. So And I mean, at low enough boost levels on the line and stuff like that, it's fine. You start going to high enough boost levels though that return pulse is going to be a high enough pressure to blow a valve open. Bad stuff happens really quick.
Right.
So like shift cut and stuff like that would be hard with your 50 pounds of boost and
Yeah.
strain gauge type situation.
Yeah, if you can keep it firing before it leaves the chamber, you're in far better shape. So if you can get it to light off at negative 30 degrees of timing or something, which really kills pretty much all of the torque, that's way better than actually turning it off. Turning it off, bad things happen real quick. The hydraulic versus solid lifter side of things, we've seen some areas where basically on a two-step where you've got a bunch of bangs going on and you may have pressure waves coming back that are big enough to start unseating the valves a little bit. We've seen a couple people running solid lifters and say that that's improved performance there a bit. But everything we've run's been hydraulic lifters. If you have a normal running scenario where you go from a hydraulic lifter to a solid lifter and something gets better, you have band-aided a problem. You have some other instability going on. If you're in a normal operating range and that makes a difference, it shouldn't. No big bangs there, that was fine. Yeah.
To go back a little bit, you're talking about the natural frequencies and how beehives get around that.
Yeah.
What is the advantage of that? What does natural frequencies, resonant frequencies, cause issues with Valvetrains?
Okay, so any spring system, think of it like you're pushing somebody on a swing, right? If you keep pushing them at the wrong time, they will never go up. If you keep pushing them at the right time, they will continue to go up. The spring has the same kind of behavior with the behavior from a standing wave going from the top to the bottom of it. So I don't have any video on it, but I've actually got, I don't have it here, I mean. I actually have video of some straight coil springs that we tested out on a Spintron kind of setup where the spring actually was jumping off the seat. You could see an 1/8 inch or so of the spring jumping off the bottom of the seat, and this was at over 100 pounds on the seat. So the resonance in the spring itself can make it have 0-4 set points during the engine cycle, and then it loses control at that point.
So where would a straight spring versus a beehive come into? Why do they sell them if they're?
Yeah. Well, in an OEM engineering point of view, you're looking at jerk, which is the next derivative of acceleration, to figure out the frequency content on it, and you would design your profile, your cam profile, and all the parts along with it that you wouldn't excite it during the operating band. And that can be a rev limit, that can be maybe an area that it just passes through quickly and you don't use much. Straight coil springs are definitely cheaper to manufacture. But there's areas that they can work in, and if you have an area where it goes into some resonance, but it doesn't go too bad, it's okay. You see, I don't know if anyone's taken apart old like V8 engines. A lot of them have dampers inside of the spring. That's to slow down that resonant activity when it starts happening.
Interesting.
Anything else? If anyone thinks of any follow-up questions, feel free to find me at the booth.
Thank you.